All right, today we're jumping into one of the most fundamental ideas in machine learning, distance-based methods. Now that might sound a little technical, but I promise you the core concept is super simple and honestly a lot of fun to wrap your head around.
So think about this for a second. We humans, we just know when things are alike. You know, a cat is more like a dog than it is like a car. But how do you teach that to a computer? How does it look at raw data and go, yep, these two are alike? This is the exact problem that distance-based methods were designed to solve.
The whole thing really just boils down to one simple, elegant principle. In the world of data, just like in our world, proximity is everything. If things are close, they're related. If they're far apart, they're not. It's an idea you already get. We're just going to see how computers make it work with numbers.
So let's put a formal definition on it. Distance-based methods are all about this idea that data points that are close together on a sort of digital map are considered similar, and the ones that are far away are different. It's kind of like a seating chart in a classroom, right? You're probably going to have more in common with the person sitting next to you than with someone all the way across the room. Computers use that exact same logic.
And this image, well, it visualizes the whole concept perfectly. You can just see it. You've got these little neighborhoods of color. The green dots are all hanging out together. The blue dots have their own little cluster, and the pink dots are off in their own corner. They're considered similar just because they're physically close. That's the one rule to remember. Closer equals more similar.
Okay, so that's the big idea. But how do we make it practical? How do we get a computer to actually do this? Let's use a really simple analogy to see how we make this whole concept of distance digital.
Just picture it. You walk up to a playground. You see a bunch of kids huddled around a net. What are they doing? Probably playing soccer. Then you see another group over by the swings. Now, if a new kid runs over and joins that soccer group, what game are they about to play? Soccer, of course. You just made a prediction based on their proximity to an existing group.
That analogy makes total sense for us, but it brings up the next big question. A computer doesn't see a playground or kids, it sees numbers. So how in the world does it actually measure closeness or distance in its digital world?
Well, here's how. The computer turns every single piece of information into a coordinate on a graph. A person's height, the price of a car, a student's test score, every feature just becomes a number. And once everything's a number, you can plot it as a single dot on this giant digital map. Then the computer can measure the literal physical distance between those dots.
So how does it measure that distance? The most common way is something you definitely learned back in high school math, the Pythagorean theorem. In machine learning, we just give it a fancier name, Euclidean distance. As you can see right here, it's just the formula for finding the straightest, most direct line between 2 points. This simple little formula is the workhorse of so much machine learning. But, and this is the really cool part, a straight line isn't the only way to do it. Depending on the kind of problem you're trying to solve, a computer has a whole toolkit of ways to measure distance. Take a look at Manhattan distance here. It's like calculating how many city blocks you'd have to walk to get from point A to point B. And then there's cosine similarity, which isn't really about distance at all. It's about the angle between 2 points. The big takeaway is that closeness can mean a lot of different things to a computer.
Okay, so we know how to measure distance. Now let's see how we can use that for our first major application, classification. This is all about teaching a computer to guess what group something belongs to.
So let's set up a super simple problem. Imagine we've got a bunch of data about fruit. Based on things like their size, their weight, and their color, we plot them on our graph. And what happens? Well, all the apples end up in one little cluster of red dots, and all the pears end up in another cluster of green dots. They group up naturally because their features are so similar.
Okay, now for the fun part. Here comes a new, unknown piece of data, this blue diamond. Where does it belong? Well, the computer does exactly what you or I would do. It just measures the distance from the new diamond to its neighbors. And since it lands way closer to the red dots than the green or black ones, the computer makes a classification. It says, hey, this is almost certainly an apple. It really is that intuitive.
So that's how we sort things into groups. But what about predicting a specific number, like the price of something, or maybe a temperature? That's a task we call regression. And it turns out distance is incredibly useful for that too.
The guiding idea here is just as simple. Just think about real estate for a second. Houses in the same neighborhood, they tend to have pretty similar prices, right? You don't usually see a giant mansion built right next to a tiny little cottage. That real-world logic is the entire foundation for distance-based regression.
So how does this work in practice? Let's say we want to predict a house's price. Step 1, we take all its features, square footage, number of bedrooms, and we plot it on our data map. Step 2, the algorithm looks around and finds its closest neighbors. Which other houses are near it on the map? And finally, step 3, it just calculates the average price of all those neighbors. And that average becomes our prediction. Simple, right? But it's surprisingly powerful.
Now, it's pretty easy to look at all this and think it's maybe a little too simple to be effective. But that simplicity is exactly what makes it so powerful. And it's why understanding this one concept is so fundamental to all of machine learning.
So why does this matter so much? Well, for one, it's incredibly easy to understand and explain. There's no mysterious black box here. Second, it's really fast for computers to calculate, which lets them find similarities in massive datasets all on their own. And maybe most importantly, this very basic idea is the foundation for tons of more complex, more powerful algorithms down the line.
And I really want to land on this point. Getting a handle on this concept of distance and similarity, it's like learning your scales before you try to play a symphony. It is the fundamental building block that so much of machine intelligence is built on top of. If you get this, you're on your way to getting so much more.
And that leaves us with one final, very important question. This whole nearest neighbor idea works really well, a lot of the time. But what happens when the data gets messy? What if the closest answer isn't actually the right one? We're going to dive into that exact challenge in our next explainer. Thanks for joining me.